Log on, tune in, find out. Another good idea from Cambridge.
So then Kroode from Shell. So Fons has a talk yesterday and has another talk, but a different one. Yes.
Amazing. Well, thanks again, and pleasure to be here. So the title of this talk is somewhat odd, especially if you know what the Kirchhoff operator is, and most seismic people in the audience will. And if you don't know, then I'll explain what it is. Typically, when we talk about the Kirchhoff operator in seismic imaging and about Kirchhoff imaging, we think about asymptotics. So we think about rays and what have you. Still, I want to transform this Kirchhoff operator into a wave equation-based one. A little bit about the motivation. So how did this work arise? It was really in an attempt to understand a paper by Paul Sava and Sergio Folmel in 2003, so it's already 8 years ago. They explain how you could construct wave equation-based angle gathers. And if you don't know how that goes, I alluded to it briefly yesterday, and I'll explain it more in detail today. In particular, if you look at Kirchhoff, the classical Kirchhoff integral, there is an angle-dependent reflection coefficient in that integral. And I was wondering, these subsurface angle gathers of Sava and Folmel, what have they to do precisely with these angle-dependent reflection coefficients? Presumably, and that's very implicit in the paper, they are the same in some sense, and I would like to quantify that a little bit better. The second motivation is really, well, since they have a wave equation-based construction of angle gathers, which is really sort of a backward type of operation, shouldn't I be able to formulate indeed the forward problem as well in terms of the wave equation? And if I could do that, I could arrive at a wave equation-based least squares procedure for angle-dependent reflectivity. So that is the aim of this talk. So the outline is really simple. I'll start in an extremely pedestrian manner. I'll take you back to your graduate days, or undergraduate days, and I'll explain a little bit about angle-dependent reflection coefficients in Kirchhoff scattering. I'll explain Sava and Folmel's construction. I'll explain what the link is. I'll talk a little bit further about that wave equation-based Kirchhoff operator and its inverse. This is as simple as it gets. You have a two-layered medium, so just constant medium parameters. This is acoustic, so a density and a velocity above that interface and other density and other velocity below that interface, and you have plane waves with an incident wave factor Kn and a reflected wave factor Kr. It's just Snell's law is obeyed, right? So it's completely trivial. The only point I want to make is that the amplitudes of these plane waves get a reflection coefficient, and that's sometimes also called a Zupritz coefficient. So I will denote that by a Z depending on theta. And there's a simple geometrical formula for that reflection coefficient. So this is just to set the scene. How do these Zupritz coefficients come into the Kirchhoff integral? So I've written down the Kirchhoff integral here. Really what you want to do, you have a situation where you have a source and a receiver and some smooth reflector, and you want to describe the singly scattered seismic data from that reflector. What you really do is you propagate with a Green's function from xs to x, that is over here, and you reflect with a Green's function from x to xr, that's over there, and then you integrate x over the reflector r, and then by stationarity the most dominant contribution will come from that point x for which Snell's law is obeyed. Right. As you can see, I'm not only integrating over the reflector but actually over the full three-dimensional space, and to make that equivalent, I have actually multiplied that Zupritz coefficient, which is just the strength of the reflection, times a singular function of the reflector. So that's just a delta function in a coordinate locally orthogonal to the reflector. Actually, seismic imaging is about, if you're just interested in structural imaging, you want to know this function, this singular function, because that is gives you an image of the subsurface. And if you're also interested in extracting attributes, then you would also like to know the Zupritz coefficient, so the angle-dependent reflection coefficient. This is a slightly more compact notation just to show that this is a classical Kirchhoff operator, and I would like to invert this linear problem. Fair enough. I need a couple of notations. Think about that the reflector has that yellow plane, the tangent plane, and think about rays hitting the point X in a plane. These their tangents form a plane. That's the gray one. Then I guess there is a normal to that plane. I'll parameterize that normal by two angles, nu1 and nu2. There's also two vectors orthogonal to that normal in the plane of the tangent plane to the reflector, and there is an azimuth vector. Right? That is, by definition, the normal to the normal in the plane of the two tangents of the ray, and it can be clearly written as a linear combination of these two basis vectors, and that actually defines an angle phi, which we call the azimuth of the reflection. Okay. Basically, if you take the slowness vector, so the tangents to the rays when they hit the point X, they are the gradients of travel time functions. If you add them up, you get 2 times cosine theta times that normal divided by the local velocity. If you subtract them, you get 2 times sine theta times that azimuth vector. So basically, the theta, the nu1, the nu2, and the phi are 4 angles that completely characterize this scattering process. It's very simple, but I thought to write it down so that you know at least what the notation is. Okay, here is Sava and Fomal's construction. It goes back actually to the notion of survey sinking that was introduced by Clark about 20, 30 years ago. So what you see, you have your seismic experiment over here, source, receiver, some reflector. So we call this the offset, so that's the distance between source and receiver at the surface. And now we are going to sync that to basically this level. And we do that by backpropagating with the adjoint of Green's functions. So we sandwich essentially the data between these two adjoint Green functions. And we call these points x minus h, comma z, x plus h, comma z, just a way of parameterizing it. Now, if you then evaluate this integral at t equals 0, you get what we call a subsurface offset gather. And I'll show you some examples. If you had used the correct velocity model for backpropagating the data, then this will focus actually at h equals 0. Okay, so in t equals 0, this integral clearly becomes this integral. And then if I substitute geometric optics approximations for g and also for d, I get essentially that this is an oscillatory integral of this form. If you look at oscillatory integrals, then typically you're going to look at stationary phase analysis in order to determine what the most dominant contributions are. So the phase needs to be stationary essentially with respect to the receiver coordinates, the source coordinates, and with respect to the frequency. So this is going to give you a couple of stationarity conditions. Stationarity with respect to the frequency is giving you the first one, and then stationarity with respect to the source and receiver coordinates, the second and the third one. You can look upon these stationarity conditions as a set of 3 equations with 5 unknowns. That's namely x and h and z and xr and xs. So using the implicit function theorem, you could solve 3, namely z, xr and xs as a function of x and h. So you see that these subsurface offset gathers, they really can be parameterized. This is rather irrelevant, of course, what the stationary source and stationary receiver contribution was, but these subsurface offset gathers they are going to look like curves of the form z of x and h. And now I would like to, of course, to calculate the derivatives of dz dh, and you can easily do that with the implicit function theorem, of course. You get this expression, and then you recall that the image focuses at h equals 0, so you evaluate this at h equals 0, then you get this. It's quickly, but it's still extremely simple, I guess. You recall the expressions that I had in the third slide or so, and then what happens, you can almost see it, I guess, this becomes the tangent of theta. So what does it mean? It means that if you construct a subsurface offset gather by survey sinking and evaluating at t equals 0, you can describe it as a function z equals capital C of x and h, and I've just given you the derivative with respect to h. So if I now do a slant stack, then essentially what's going to happen, so a slant stack in the direction k, and this is going to peak for k equals tangent theta. And that's all there is to it. Brilliant idea. Took me a long time to understand it, I have to admit. But this is what it is. And here are a couple of examples. I guess I already showed a few yesterday, but this is it's a 6D model again. Synthetic seismic has been imaged in the perfect model, so this is the perfect image. And then you look at these subsurface offset gathers. Oh, that is not what I wanted to do. You look at these subsurface offset gathers for one x location, so this is the h, the subsurface offset, and you see, yeah, they almost perfectly focus indeed at h equals 0. You can do the slant stack, you get that angle gather for k equals tangent theta. They're perfectly flat.
Sorry, I missed what a slant stack was.
A radon transform. Yeah. Sorry. Yeah, I know you criticized me about all the jargon, and but
you have to say it in a different jargon.
yeah, yes, that's what it is. Okay, so this is nice. Couple of other examples. I've now added surface multiples in this modeling. You see, there's some sort of funny things happening in the image, right? All these stuff here that's contamination by the multiples. You also see that, yeah, you still see the primary reflections focus perfectly at h equals 0, but those multiples, they don't. And in the angle gathers, you see that they curve like this. They have RMO, move out, curvature. Another game that is important, of course, what if we did not use the right velocity model to do this survey sinking and to produce these images and these image gathers? Well, you see the image gets much worse, but also you see on the left, they're not focused at all, the subsurface offset gathers, and the angle gathers are curved. So these are all, you can use these things in various manners. Sometimes you could think, well, if I'm sure that the velocity model is correct, I could get rid of the multiples by just some sort of filtering. If the velocity model is not correct and I know that I have no multiples, then I can use this for velocity analysis. That's the way we go about. I need some assumptions to state my main results. The first two are very, very well known in microlocal analysis. You don't want rays that, when they impinge on the acquisition surface are tangent. We call that grazing rays. You also don't want scattering over 180 degrees because that's when a reflection problem transforms into a transmission problem. You want to basically separate these two. There's a couple of more special restrictive assumptions that I would very much like to do away with, but I have never been able to do this so far. I know that other people like Bill have looked at it, so there may be ways to overcome these. So in particular, I don't want any turning rays in my model. I don't want rays essentially when they start downwards, they need to keep going downwards all the time and don't have horizontal or overturned segments in their ray path. That's a serious restriction because in practice that happens. And also the way I parameterize it with horizontal subsurface offset gathers, that doesn't work very well with vertical reflectors. Okay, I'm getting ready to do my first result, and I'm going to formulate it in a set of operators that form a commutative diagram. So here I have my angle-dependent reflectivity, and I've sneakily introduced the azimuth as well. For an isotropic acoustic problem, reflectivity doesn't depend on azimuth, but I'm sort of anticipating that I might want to do anisotropic stuff, or my illumination might not be perfect, so you get azimuthal effects into that. Anyway, this operator K can be trivially extended to the case of azimuthal varying media. That's not a problem. The other effect of this is that there is now quantities over here that depend on 5 variables, x, y, z, and 2 angles, theta and phi. And the data, as I explained yesterday, is also in principle 5-dimensional, 2 receiver coordinates, 2 source coordinates, and a time coordinate. So at least you get something that might be invertible. I need to explain what these pseudo-differential operators are. These are essentially vertical derivatives with respect to the source coordinates, receiver coordinates, and of course a simple time derivative. But how do you do a vertical derivative with respect to the receiver coordinate if you only measure along a horizontal plane? That can be done like this. If I can find my mouse. So just you go to the Fourier domain, the spatial Fourier domain, temporal Fourier domain, and you multiply by the square root of omega squared over the local velocity squared minus the horizontal wave number squared. This turns out to be equivalent to a vertical derivative. What is this operator I? Well, we already saw that. That's the subsurface offset generator or operator or whatever. So it takes data, does its survey sinking, and that evaluates at t equals 0. H is a horizontal vector, so it's in the h1, h2 direction here. I gave you a 2-dimensional example when I talked about Sava-Fomal's constructions. Here is my slant stack. So it's a slant stack in the 3rd direction. K is a horizontal vector, has components k1 and k2. Notice there is a somewhat funny normalization that I had to choose to make everything commute. So nu1 is related to the dip vector that I spoke about. So the procedure becomes dip dependent, and rho is of course the density. And then finally, this tells you how k, the subsurface wave factor, depends on theta and on phi. So for the 2-dimensional case, this was just k equals tangent theta. And now I need to bring in the azimuth, and the formula is more involved, but can be done. Notice that it is again dip dependent. Okay, here's the diagram again, and a statement, namely how to reconstruct the angle azimuth dependent reflection coefficient from primary reflection data in a known velocity model. So if you give me data that is the result of acting with k on r, primary data therefore, in a known velocity model because k depends on the velocity, then by walking through this diagram I can reconstruct them, the reflectivity that is. So this is just a set of pseudo-differential operators, Fourier integral operators, to reconstruct the angle-dependent reflectivity, the angle azimuth-dependent reflectivity. So I guess that when I figured this out, I was happy because I finally understood what these angle gathers had to do, the angle gathers that Sava and Foma had constructed had to do with angle-dependent reflection coefficients from physics. You could also say this is a true amplitude imaging formula for angle-dependent reflectivity. Maybe this could have been derived really quickly from Sava's and Fomal's paper, but it wasn't clear to me. The next game I want to play is I want to take that diagram and only concentrate at the top half. So I'm going to concatenate these operators. And I'm going to call the concatenation k tilde. And here is my wave equation-based Kirchhoff operator. I was able to show that this guy has a very simple and maybe very unsurprising integral representation. Namely, it's formulated in terms of, so it acts on a subsurface offset gather and it maps that into data. You need to take the vertical derivative of the subsurface offset gather and then you sandwich between Green's function, you integrate over the coordinates in the extended image space in essence, and then you get data again. So I'm almost done. I've explained my title at least, right? So it's the rest is yeah, just some fiddling around. I can also concentrate at the lower part of that diagram, basically concatenating these through the differential operators and this Fourier integral operator. And you will not be surprised that if you do that, then the dt becomes a minus I omega over here, and these vertical derivatives, I can actually let them act on the Green's functions that I used to construct the to backpropagate, to construct these subsurface image gathers. Since you, in a wave equation calculation, you calculate them anyway, and it doesn't really matter. It's very easy to do the z derivatives, I guess. So this isn't very special. What you then end up with, so if you now forget the whole diagram, but just take these two formulas, so k tilde is the modified Kirchhoff operator. It's actually a Kirchhoff operator in disguise, right? I've traded the reflection angle and azimuth for two subsurface offsets, h1 and h2, and okay, forget, I can always go back to the angles if I want to by a radon transform and a transformation from wave factor to angles. Right? So, but this is, so k tilde goes from extended image to data space, and I tilde goes back, and I've argued that if D is primary data, then the k tilde and I tilde are each other's inverse. Now I want to know, of course, what if D is not primary data? Or what if I was using the wrong velocity model? What can I say about the composition between k tilde and I tilde? I need a map from cotangent, the cotangent bundle, data space, a cotangent bundle of this extended image space to describe that. So if you think about data space, it's really a set of receivers, sources and times, and the cotangent bundle, yeah, you have then of course also wave, momenta associated to these. So I'll call these kappa r and kappa s and omega. And if these are in so kappa r squared is smaller than omega squared over c x squared, then you can basically from the knowledge of the horizontal component always reconstruct the vertical component as well. This then defines the tangent to a ray emerging from this source location, and you can follow it downward. And the same you can do at the receiver location. Now you specify a total time as well, that is over here, and if the rays keep going down, they don't overturn at some moment, then there is a well-defined map that basically tells you where to, at what depth time is up, so to speak. And at that depth you intersect the rays and you call the intersection point x minus h and x plus h. And then you have local slowness vectors. I call those E alpha and E beta, and I can also now form P's as omega times E alpha plus E beta multiplied by S plus and S minus. S plus is a slowness vector, so in x plus h, and S minus is a slowness vector in x minus h. And the horizontal component of k is just the difference between these vectors. So this map is easily constructed. What can you say about it? It's actually a diffeomorphism from a conic neighborhood in the cotangent space of data to a conic neighborhood in the cotangent space of extended image. And these conic neighborhoods are described over here. So this is pretty simple. This is actually the condition that there are no grazing rays, no rays that are really tangent to the acquisition survey. This is somewhat more mysterious, this condition, but it is just, so I had constructed the map M in a picture, so in words, so I should be able to calculate the image of that map, and that's what I've done, and this is what you get. I'm almost done. Okay, now using these notions, I can now formulate these results. So I tilde and k tilde are almost each other's inverse. They are more precisely on distributions that have their wavefront set contains in these regions omega x and omega y. They are to the differential operators, and you see their symbols that are essentially apart from the characteristic function on this omega x and omega y. They are given by this quantity. This is an interesting one. S is the slowness. S plus is the slowness in x plus h. S minus the slowness in x minus h. E alpha and E beta were the tangents to rays in those locations from the surface. Now imagine what would happen if we were dealing with primary data and the image would focus at h equals 0. Look at the amplitude here. At h equals 0, S plus and S minus are equal to each other, they're just S. And everything drops out, right? It's just 1. So what you see is that for primary data, yeah, they are each other's inverse, and if we're not doing primary data like multiples, okay, it's a to the differential operator, so they, if you go up and down, they get multiplied by a pseudo, and I have the amplitude over here. So this is the well-known notion, like if you migrate data and then you demigrate them, that's a lot of jargon, but you understand, then the kinematics does not change. The amplitude does, at least for non-primary data. So these are my conclusions. I think they're fairly obvious. So I've adapted Sava and Fomal's construction slightly to arrive at angle-dependent reflection coefficients, the true angle-dependent reflection coefficients from physics. I've shown you that there is a wave equation-based formulation of the Kirchhoff operator, and I can now use that, of course, to estimate these extended images in a least square sense. If you, after all, have a forward operator, then you let it act on an unknown I, and you minimize the difference between D, the data, as observed, and K tilde on I. And I've talked about these compositions and shown you what they look like. Thank you.
Thank you. So we have time for questions, please.
EZ, the vertical derivative, that's set up with the turning ray business.
Sorry, the vertical derivative, what's that?
The reason why you rule out the turning rays is you get a square root singularity in the symbol. I presume what's going on.
Well, all sorts of things break down. If first of all, that map M is not, you cannot do it anymore, right? So that's the, let me go.
Oh, it's the grazing rays. It's only at the surface.
So this you want to basically go from travel time to depth in order to say at what location these rays intersect. So what is the ax actually? And therefore you need to have the rays going down continuously, because if they would go up, down and then up again, they would have 2 intersection points. I guess that it would be lovely to try to change that. You'd likely have to change the direction of the ages and whatever, but I don't know how.
One suggestion about that, I think, also lies in the work by Roel Sneeder in the 80s, And then for Mel and Sava with the Riemann extrapolation. So if you define a reference wave field that gives you a conformal map, you have a better chance of handling certain directions. At least directions for vertical reflectors, for example.
Okay.
Maybe for not all of the points in the vertical reflector, but maybe for deeper vertical reflectors, they might be at least easier to incorporate. The differential geometry would be messy, but there'd be lots to learn from what they've done.
Okay, would appreciate a reference. I'd love to extend this work indeed.
The other comment I had is that we can now acquire data that has pressure in 3 components of particle velocity in marine.
That's right.
So your measures for KR and KS. KS not so much because we still don't have three component gradient sources.
Who knows?
But for KR,
you have a direct measurement rather than, yeah. Good point.
It's fascinating to observe that more or less contemporaneous with your work, Chris Stolk provided an extremely similar construction for
Really?
the single shot case.
Oh, okay.
Where it's another determined problem. You get very similar construction, DZR, but not DZS because it's
there's only one shot.
fixed.
Yeah.
Otherwise,
So
very,
that's
very close.
it's a stacked, you're inverting for a stacked image then, I presume.
No, not for a stacked, single shot inversion.
Okay,
So-
okay, it's not stacked, no, okay.
It's a correction of amplitudes for migration of one shot profile, if you want to think of it that way. But it's fascinating, very parallel.
You talk to. Thank you.
Another comment in the same sense, when Gilles Lambaret derived some sort of true amplitude for the one-way wave equation, then it had also exactly the same Z
There's a Z
derivative.
derivative as well,
on
I've
the
seen
Green
his paper, yeah. I guess that there are many ways to Rome, and most of us have found one. Thank you.
Maybe another question is, so you were able in the exact model to derive an inverse of the operator. Is it exactly an inverse up to smooth terms?
Yes.
Or, yeah.
Indeed. Yeah.
Okay, thank you.